you have to have video. Start video.
Mackenzie,
Yes.
Kyle's at my house and he's going to share my laptop with me today.
Okay.
But I just noticed that I didn't even take quiz 4 from last week. Is there any way that you could open it up and I can take it today?
Quiz 4 in materials.
Yeah.
Downstairs. We're good. Alrighty.
Yes, I will give it until midnight tonight.
Thank you.
Oh, well, it should, the owl should like spin around to you.
Hi, Christy.
Is the owl working?
It is.
Okay. Joe just walked up here. He's like, I want to make sure she can see me. And I was like, well, if you talk, it should spin around to him, right?
Yes, it should. It should automatically look at wherever the voice is. So as you stop talking and he talks, it should switch to him.
Say something again.
Hey, Mackenzie, I am present. This is Joe.
Yes.
Yes, ma'am. I'm here.
Can you talk just a little bit louder, Joe?
I just wanted you to know I was present is all.
Okay.
All right.
Awesome. I'm just getting ready to do attendance. I was putting the live stream up on YouTube. And now I'm going to do attendance. Okay.
Moving, but Joe, Jennifer, Kaden, and Cattell are here.
Joe, Jennifer, Caden, and Cattell. Okay.
I really like how the background makes your head look like it's pulsating.
I know. How smooth and.
Yeah. The integrated webcam in my laptop is not always. Okay. Is Connor online? Okay. Marcus? Good morning.
Mackenzie, I'm also here.
Great. Thanks, Kyle. Is Porter online? Okay, great. Lynette?
Here.
Great. Sam? Good morning. Jack?
Good morning.
Hello. Kyle, I already heard you're here. Amber? Great. And Haley's online. So one thing, this shouldn't really affect anything for you guys, but on attendance, I added a category for online. ISU asked the instructors to facilitate contact tracing. We need to be able to say who was actually in class and not, in case you're around somebody who has a case of COVID. So I added an option that said you attended online. It has the same amount of points as being present. So it shouldn't affect your grade at all. But if you guys see anything weird, change, because sometimes Moodle doesn't do what I expect it to do. Let me know. But you should be getting full attendance points when you are online. It should just mark you as being online instead of present. But they're the same amount of points. And that way, if we do have somebody who's in a classroom who has COVID and we were all around them, we know who needs to then isolate versus who was attending from home and is not exposed. So all of the classes have that added now, just so you guys are aware. Okay. I have started looking at the material studies. It looks like you guys have a pretty good handle on corrosion and what's going on. The papers are looking pretty good. So that's great. I will hopefully have them graded, all read and graded by the end of this week. But today we're going to review for the exam, excuse me, which is on Friday. So let's start with some definitions. Who remembers the definition of an isotope?
What was that, Mackenzie?
The definition of an isotope.
That is an element, it's an element with different number of neutrons.
Correct. An element with different numbers of neutrons, but the same numbers of protons. What is an isotone?
Good question. Isotone.
Are you be allowed to have her chart of the nuclides on the test?
Yes, you will.
An isotone is
Kenzie, isn't an isotone something with the same number of neutrons but different protons?
Yes. That's correct. Everyone hear that one? Isotone has the same number of neutrons, but different numbers of protons. What is an isobar? Anyone remember this one? Sorry, reporter, I didn't see your answer till after I heard Jack's. Okay, so an isobar is
Two or more isotopes of different elements with the same atomic weight.
that is correct. But when we were looking at the chart of nuclides and we were looking at those numbers, it's different atomic numbers, but same mass number. Okay, what is oxidation?
Isn't that when an electron from an electrolyte takes, I don't know, a part of a metallic atom?
Say that one more time, Joe.
It's when an electron from an electrolyte takes part of an atom of metal, like a proton. I'm not really sure about that part.
You're very close.
Isn't it when an atom loses an electron?
Yes. Your atom is going to, your metal is going to lose an electron to the ions in the electrolyte.
Can you repeat that?
And what is reduction?
Never mind.
Hey, Mackenzie, Cattell has a couple questions.
Okay. It seems like the owl is very low volume because I'm having a hard time hearing you guys. On the bottom of it, there's a plus and a minus. That's the volume that you can turn up if you
I
would
don't
please.
think the owl's plugged in correctly.
You're ignoring me.
There's the plus and the minus.
Is there a power button?
And if it's not following your voices, you guys can turn it to so that its primary screen faces the classroom.
This?
Yeah.
No, don't do that.
Why? Because you didn't brush your teeth today?
No. because I don't wanna see you before I go.
Don't play on your phone then.
All right. Go ahead, Cattell.
I just wanted you to repeat that, please.
Okay. Oxidation is when the ions in an electrolyte remove electrons from a metal.
Thank you.
And then Haley answered the reduction question. It's the chemical reaction where an atom gains an electron. That's correct. Reduction is essentially just the opposite of oxidation. Is general corrosion.
Slow, uniform removal of material. The surface of the material.
That is correct. It's slow and relatively uniform. If I showed you a picture of corrosion, would you be able to pick out what is general corrosion, what is pitting corrosion, and what is galvanic corrosion?
Yes.
Can you explain the difference between the general and the galvanic?
Yes. Galvanic is two dissimilar metals in contact. Corrosion occur because of that contact. So a picture of galvanic corrosion will always have two different metallic items. So a joint, a bolt on a sheet of metal, a connection, a valve with multiple metals, something like that. And one of them will not be corroded and the other directly around the contact area will be corroded.
Mackenzie,
Yes.
the definition of general corrosion.
General corrosion is the relatively slow, uniform removal of material.
Thank you.
And I will add that it's important to remember that this only occurs in a specific environment. And we talked about there being two conditions that are required for corrosion to occur in our lecture slide. Does anybody remember what those environmental conditions were?
Metal and water in the same environment. And there has to be a chemical reaction between the metal and water to form an oxide.
Does everyone agree? Or anyone have a different one? Okay, so that is correct. You have to have metal and water in the same environment. And then you have to have a chemical reaction between the metal and water that forms an oxide. So it would be very correct when you discuss general corrosion that this is the relatively slow, uniform removal of metal in a water environment through an oxidation reduction reaction. That would be the most technical definition there. And that is correct, Haley. Water temperature does increase the rate. There's a couple other things that increase the rate of corrosion. Anyone else remember some of the others?
Like flow rate.
And what effect does flow rate have?
I want to say higher flow rate, but I remember us talking about lower flow rate creates like an air pocket, which introduces oxygen into like a pipe. I'm not for sure on that one.
So general corrosion increases as water velocity increases because that movement of the water tends to remove the protective oxide layer and cause some erosion. Remember in the lab we did for components, there was an erosion corrosion example on one of the pump pieces in the little cart of damaged pieces. So you can have water velocity increasing. And remember we talked about 30 to 40 feet per second is usually where we start seeing erosion. But then we also talked about essentially low flow or stagnant flow, which increases pitting corrosion. So the same effect in the plant, water velocity, different effects depending on if you're talking about different types of corrosion. And it's important that you understand why, right? Our high velocity is removing our oxide layer. And so when you have a uniform issue, that faster water is going to start causing some erosion, which is going to remove some of the metal surface, which then makes it easier for the ions in the electrolyte to get close to the metal surface and create that oxidation reaction. But remember, we talked about the fact that when rust first starts and it forms that oxide layer, it's self-inhibiting. That oxide layer protects the metal and decreases the corrosion that's happening overall. But if the water keeps flowing by very quickly and removing that oxide layer, the metal is going to keep oxidizing to recreate that layer, the state it wants to be in. And every time the water removes that layer, it's taking away some of the metal atoms. And so you're going to have general corrosion. When we're talking about pitting corrosion, it's localized accumulation of oxygen, resulting in localized attacks on the metal surface. And essentially, the anodic site, the area where corrosion occurs, becomes fixed in a small area, and there's deep attack holes on some place that otherwise is not experiencing general corrosion, right? Several of you were really surprised that there were those pitting holes in the damaged pieces on the cart in the components lab. But remember, pitting corrosion generally occurs where general corrosion does not. And so the fact that you see those holes without rust around them would be normal, right? And so for pitting corrosion, if you have a little pocket of low or stagnant flow that oxygen can accumulate in, it's going to deep attack the metal instead of create that uniform oxidation layer and then have the water rip it off. So two slightly different mechanisms at work in those types of corrosion, even though the fundamental thing still happening is an oxidation reduction reaction. Does that make that clear?
Yeah.
Everybody online? You tracking?
Yep.
Okay. Great. Okay. What is an electrolyte?
The fluid that conducts electricity.
That is correct. There were also a couple of definitions from our chemistry review that I would make sure that you guys are familiar with. Acid, base, salt, solvent, alkane. We'll be discussing these in different applications as we get into more of the materials. But a general definition for those. See. Yeah, there's a list in that volume 1 of the, list in volume 1 of the DOE chemistry handbook. Acid, base, salts, alkanes, solvents, there's a few other things on it. I'd be generally familiar with what those are. You don't have to have like the specific technical definition memorized, but understanding.
Mackenzie,
Yes. You muted again, Haley.
Could you repeat that list when you have a moment?
Sure. Okay, I will put this in chat. So acids, salts, bases, alkanes, solvents, mixtures. I am reading you a partial list of the items that are described in that first section of volume 1. You don't have to have these memorized. I'm not going to give you a list of those chemistry terms. This isn't a chemistry class, even though a lot of chemistry is involved. But have a general idea of what those are, because we will need to have a general understanding as we talk about other materials processes. So they were a good overview. So have some familiarity. What is crud? Didn't quite hear that.
Foreign materials.
That is correct. It has a specific definition, though, that's related to corrosion.
Corrosion-related something deposit.
Chalk River unidentified products.
That is what the acronym came from. But essentially, CRUD is corrosion products in the form of finely divided insoluble oxide. So it's very, very tiny particles of the oxide formed as the metal corrodes. So for steel, typically it's the iron that corrodes. So ferrous oxide would be the corrosion product when it's very small and finely divided and floating in the water. It's crud.
So it's finely divided particles that are suspended in water?
It doesn't have to be suspended in water, right? It could accumulate in a drain and it's still crud, but it is no longer on the surface of the metal. It's separate from the material that's undergoing corrosion.
Can you repeat the definition again, please?
Yes. Corrosion products in the form of finely divided insoluble oxide. Could you guys describe and compare and contrast ionic, covalent, and metallic bonds?
Ionic bonds is when they share an electron or share electrons, right? Or, yeah, kind of like a compound. Salt.
So being able to describe how they form and the physics essentially of what's happening with the electron in these different reactions will be definitely on the test. So do you understand the differences between and the mechanisms of ionic, covalent, and metallic bonding? Then describe the factors that affect corrosion. We talked about this a little bit with water flow and temperature, but understand how we typically control these in a nuclear power plant, right? We want to avoid stagnant flow areas where oxygen accumulates. We want to keep our flow rate below the 30 to 40 feet per second. We want to remove oxygen by de-aerating our water. We want to avoid leaks that allow air into our water piping and systems. And we can also force oxide layers by oxidizing materials before we install them. And then there's a couple others in the lecture, the corrosion #2 lecture, that we talk about as ways to prevent different types of corrosion. If I asked you all to draw an electrochemical cell and label the correct ions associated with the electrolyte and the anode, could you do it?
Nope.
Okay, let me pull up an image then, so we can look at that.
No idea what that is.
What about that?
Okay.
36.
Okay. So here, this is specifically corrosion of iron. And so they've labeled the ions leaving into the electrolyte as iron, Fe++ ions. You don't have to pick a specific metal and specifically label the ions, the positive ions. You would just need to know that you have a metal in contact with an electrolyte, that the metal is an anode and it's going to have electrons, and it's going to be losing the positive ions into the electrolyte. And this is the chemistry DOE handbook, volume 1, page 3 of the module on corrosion, which is module slow. I guess it doesn't say. Module 2. So corrosion theory, electrical chemical cells, right here. We have this figure. It does tell you a list of metals here and what ions are formed, but you don't have to memorize this. You can just label this as metal, electrons, positive metal ions, and your electrolyte. And that would be sufficient. Okay. Does that help, Joe?
I forgot what I even asked you to begin with.
I asked if you all could draw an electrochemical cell and show the correct ions associated with the anode and the electrolyte. And your answer was no.
I wasn't the one that said no, but I couldn't do it either.
Oh, I'm sorry. I thought that was your voice. My bad.
When in this electrochemical cell problem, you're saying that the metal is an anode, it has electrons, and it is losing protons? Is that what you said?
No, it's not losing protons. It's losing cations. So it's losing parts of the metal that are positive because they are short electrons.
Okay, thank you.
So those electrons are staying in the metal, and that's what's forming the anode. And the pieces of metal that are now positive because they lost an electron, they're bonding with the oxygen in the electrolyte, and they're leaving the metal, which is what causes the corrosion.
On this test, we get a sheet of notes also.
I'm sorry, I heard you say on this test, and then you cut out a little bit.
We get a sheet of notes for this test.
No, you won't get a formula sheet for this test, but you do get to have your chart of the nuclides.
We can use all the information that's in there.
Yes. Mhm. Which, speaking of the chart of nuclides, if I asked you to find an element and determine its half-life and modes of decay, could you do it?
I think so.
Think so? Okay. I believe that the videos where we went over the chart of nuclides, I did not post. But if you guys would like, I can put those up. Oh, no, it is. It's on Moodle. The nuclides lecture is under week 1. But I can put under week 2 the additional stuff we did with the chart of nuclides up on Moodle so you guys can review that. But yes, be able to determine half-life and decay modes, be able to follow a decay chain, be able to identify a stable isotope so that you know when to end a decay chain. And then be able to understand as certain reactions, alpha decay, beta decay occur, what nuclides are formed in each step of that decay. And know how to find the number off the periodic table in the back of the chart of nuclides so that you can quickly find different isotopes in the chart of nuclides instead of just flipping through the book looking for them. That will definitely help you with time management on the exam. What are the particular concerns that nuclear power plants are focused on when it comes to pitting corrosion? Are you raising your hand, Jennifer?
No, scratching my face.
I'm sorry, I couldn't hear you.
Oh, scratching my face. But
Okay.
I'll answer it if you tell me again.
Anybody online? What's the particular concern we have with pitting?
Moving parts.
Order. Cavitation is going to occur in pumps when we suddenly change the pressure on our fluid and essentially the vapor and water stop mixing, and then the little vapor bubbles collapse and essentially have miniature explosions inside the pump. Crevice corrosion is a type of pitting that's very specific, but that's not the overarching concern. And stress corrosion cracking is not the same thing as pitting corrosion. Stress corrosion cracking is associated with either caustic or irradiation damage on the metal that allows that metal to crack. Are you raising your hand, Caden?
Yeah.
Okay.
Does that have to do with like pressure of a system with pitting? If it's pitted, that it decrease the metal layer very thin and it could burst.
So we are worried about how thin the metal layer gets. So the specific concern with pitting corrosion is that it is relatively fast at destroying a large thickness of metal without necessarily having other indicators of corrosion that would alert us to it happening.
Oh yeah, that's right.
Essentially, hit through your pressure vessel in a small area in a short amount of time without any of the normal water chemistry systems that are looking for corrosion having a signal, right? We have this oxide reaction and this electrochemical reaction, and we are able to do things to detect that and prevent it. But if we get a little pocket that's only happening in that small concentrated area, it may not be happening at a large enough level that it will affect our water chemistry on a bulk level that we can detect. And at a very short amount of time, it can burrow its way right through a pressure vessel. That's why the incident that occurred at Davis-Besse, where the pressure vessel head was nearly corroded through, was such an industry shock because they were monitoring their water chemistry and they did make some mistakes, but largely it was unfathomed that quickly that amount of damage could happen. So pitting corrosion is of particular concern because a very large amount of thickness can be damaged in a short amount of time without many indications that it's happening. Everyone get that? Am I cutting out? Should I write it in chat? Okay. good. Okay. Corrosion in aluminum. What are the special concerns associated with aluminum corrosion?
Yeah. Say, what are the concerns with aluminum corrosion?
Yes.
I thought they used aluminum because it doesn't corrode, well, that much.
That is correct. It generally does not corrode. And the only times it does corrode are when there are significant impurities, which is why we ensure that the aluminum we use, because it's commonly used as our fuel cladding, because it doesn't corrode, but we have to ensure that our alloy of aluminum is free from essentially the pieces of metal and other things in it that we don't want, impurities. So we specifically choose aluminum because it doesn't corrode. But if our alloy has impurities, it can. And so when we're doing something like putting aluminum as our fuel clad, putting it over our fuel in order to trap fission gases and radiation, we have to be very certain that we have a very pure aluminum alloy. We also talked about some specific concentrations of nickel that can make stainless steel more susceptible to stress corrosion cracking. So I'd be familiar with the fact that, again, one of the things that we do to protect against corrosion is we control the makeup of the material. So on that corrosion 2 PowerPoint, it talks about how stainless steels are especially susceptible to stress corrosion cracking. And so essentially, we don't allow certain ranges of chromium and nickel in our nuclear grade steels. So similar concept to just not allowing impurities in aluminum. We also will control the mixture of metals in a stainless steel. Okay, describe passivation.
Those are
What
like,
was that again? man?
Describe passivation.
when you add like inhibitors to the water makeup, so corrosion is slower, to slow down corrosion.
Yes, essentially, you're creating a material that is passive to corrosion, that's less likely to corrode by having an oxide layer on the metal or inhibitors in the water that make that corrosion reaction just less likely to happen. So passivation can occur with essentially a man-made oxide layer on the metal or inhibitors in the water so that you have a metal electrolyte environment that's more passive when it comes to corrosion. Yeah, Caden.
Oh, are those inhibitors that you add to the water, are those oxides as well?
They can be different materials. When we talked about passivation in the slide, we typically want to remove chlorides and oxygen. So it will be potassium chromate was the example. They undergo a reduction. Passivators undergo a reduction at the metal surface so that they create a layer of absorbed oxygen right against that metal. So it's not that you put in oxygen, you put in things that tend to react and absorb an oxygen. So the example we have in our slides is potassium chromate. Does that answer your question?
Yeah.
All right, guys, I will post this list of topics and definitions that we reviewed from. There's not going to be a lot of calculations. There are going to be some definitions, so do make sure that you have definitions, some of the important ones that we called out, memorized. But I'm really going to be asking you a lot to think about corrosion happening in the plant, what's happening, what does the operator need to do, what things are we checking to ensure that our systems that reduce the likelihood of corrosion are working correctly. So it's not going to be a huge chemistry test. I do want to test that you are understanding the mechanisms that are occurring with corrosion. Any questions on the test before we end for today?
I have a question. What should operators be knowing when it comes to corrosion? What should we be doing? What's the big thing?
So we're going to be monitoring temperature, flow rate, and chemistry of our water to ensure that they're within the specified ranges that are designed to prevent corrosion from occurring. We're going to try to reduce instances of tensile stress on metal so that we don't get stress corrosion cracking. We're going to replace components exposed to high radiation so that we reduce our irradiation assisted stress corrosion cracking. We're going to avoid accumulation of oxygen through ensuring that our piping systems don't have leaks and that they don't have pockets of stagnant flow where oxygen will build up. We're going to ensure that our deionizing system, deaerating systems, and our other chemistry control systems are functioning appropriately. It's entirely possible that you could be an auxiliary system operator and the only system that you are responsible for is a deionizer, right? And that goes through a particular chemical process. The coolant, as it's going through its cycle before it goes in the reactor, is going to go through this, and your job is just to make sure that certain parameters are checked, on that system so that it can actually help remove the likelihood of corrosion. So all of those factors that control corrosion are going to have methods that we monitor them. And essentially, operators will ensure that those conditions are being removed or added as appropriate, right? We're adding in passivators, we're removing oxygen accumulation. Does that make sense, Joe?
Yes, ma'am.
Okay. So Haley asked about the other classes today. Evan would like to do the lab in the 2 groups like we've been doing. So the group that's supposed to come in at 11, just go right down to the downstairs lab. Don't come to the classroom for anything. And then the group that comes in at noon, just go straight downstairs. He's got a lab all ready for you guys where you're going to learn about essentially pump curves And you're going to use some of the small pumps in his lab and look at efficiencies and how well pumps work. So it'll be a good hands-on components lab to continue your familiarization with pumps. And then for conduct of ops, we are having class today. You don't have to be physically present in the at ISU, because we're going to be talking about an assignment I put up where you're going to look at some control rooms, and instead of discussing, you know, our mock control room and its setup, you're going to essentially find some pictures online. But we're also going to be discussing logs and round sheets. And Christy is going to give you each a logbook. And we're going to practice keeping narrative logs as a homework assignment. So if you don't come to campus today, which I mean, I guess you need to for the components lab, but if you don't come to conduct of ops in person, you'll just need to find a notebook of your own and create a logbook, or pick that up from her later today. But if you can be there, it'd be a lot easier on Christy to just give you all your notebooks then. I am not sure. You can send her an email. I told her she didn't have to be available to start Zoom for the components class. So she might be working on her own classes then, but she might also be doing that from Gail's office. I'm just not sure. Any other questions?
We were just talking about you.
Oh. I'm bringing in their operator.
You what?
Did not hear it too. I have their operator logbooks.
Oh, okay.
In case I'm not here at 2.
Okay, yeah. A couple people were asking if you'd be available when they come in for the components lab at 11 and noon. If they could pick it up from you then.
Isn't it 10?
Sorry, you're right. 10 and 11.
Yeah, at noon I'm supposed to be down at the Lillibridge building,
Okay.
but
So-
I'm until then.
If people are coming in for a lab at 10 or 11, could they pick it up from you then?
Yeah.
Alrighty. Well, I have the first year's class, so I'm going to go ahead and end our class here, and I will see you guys all at Conduct of Ops.